Get your notes out. All right, now look, it's actually going to take us 3 days to complete this lab, but it really isn't 3 days of actually doing the lab. Today is going to be mostly notes and setting up or mixing up our first chemical we need, the primary standard. So tomorrow we'll do a titration to get our secondary standard, and then finally, well, you have a double tomorrow, right? Yeah. You might be able to do. You'll probably be able to do both that titration and the next one in one period. The other class we'll have to do it probably over the course of 2 periods because they spent some of the time setting up for you guys, as you can see back there, and you'll spend probably some extra. Well, they actually might end up doing because they'll have a double on the other one.
This one, I have enough space to put the notes in.
Take them down. I don't know. It's close.
Sure. That means yes.
It'll be close.
Yeah, that'll be good.
All right, look at it. We've done titration labs before. You may remember. Take a look over here. Look at this picture. Now, you don't have to draw. Just watch. Just want to go over. In a nutshell, I can tell you what a titration does, and you'll remember it right away. Okay? We did a titration for the Tums and Rolle's lab. We did a titration for the strong acid, strong base lab. All right, so we did a couple of them times, and we've used the burettes before too for other things, but not for necessarily for titrations. Say, for example, I have this burette filled up with an acid. You're going to be doing this by tomorrow, and the other burette filled up with a base. Now, let's say I know the concentration of the acid, and I know that concentration is like, let's make up a number. Say it's 2.0 molar, right? And I draw off maybe about 10 milliliters of that acid. Now, let's say I then move my thing over, my Erlenmeyer flask over. I have my indicator in there. Remember, we have phenolphthalein for our indicator. And we start drawing base off. Let's say it takes twice as much base. Let's say it takes 20 milliliters of the base to neutralize that acid until it turns color. What does that tell you?
It means the molarity is less.
Right. It means the molarity of this is less. By what factor? If it takes 20 milliliters of this and only 10 of that.
By half, so it's 20.
So basically, this guy is going to be half as strong as that guy. If I know he's 2 molar, what's this guy? Yeah, and that's all it is. And any titrations like that. You do titrations like this if you have a pool or a hot tub, a jacuzzi. You have to get some of the pool water and add. I mean, there are some nowadays. I guess all you have to do is put a little strip and test the pH. But I remember the pool we used to have. You had to add certain drops and count how many drops it took to change the color, and then you knew whether to bring the pH up or the pH down. So that's what a titration is. That's what we're going to be doing. What we're going to be doing, last time we did it, was for a strong acid and a strong base. This time, we're going to be doing it for, whoops, that's not right. We're going to use vinegar. Actually, it's not going to be vinegar. It's going to be a solution of acetic acid. And we're going to use a strong base and a weak acid. And you're going to find that it looks a little different. And we're going to do something else different about this guy. We're not going to use an indicator. We're simply going to take the pH with a pH meter every milliliter of base we add. That will be tomorrow sometime during the second titration. The first titration will be for a standardization. But let's just give you a note. Now that I've explained what a titration is, you remember perhaps from last year, little bit of notes on this, okay, just so you have it. It's the process in which a known solution is added to an unknown to determine the unknown's concentration.
I have to do that at the Y. I'm a lifeguard, so I work at the pool, but to test like the chlorine.
Mm-hmm. That's right.
pH is easier. You just have to match it to the color.
Yeah. So for the chlorine, you do a titration?
Yeah.
Yeah. So that's not unusual. So you have the unknown as your pool water, and then you add something that's known to it, probably some standard you have in a bottle.
Yeah.
I don't know what that would be. I've never done it. But anyway, that's what we'll be doing tomorrow. Actually, starting today. The reason it takes a little longer for today is we're going to do this lab, and that's why it's going to take about three periods. All right. This is not going to be your typical lab. In a typical lab, what do? We take everything's set up for you back there. You need a bottle of 1 molar hydrochloric acid. It's right there. You need a certain concentration of sodium hydroxide. It's right there. That's not how labs are done in college. I hate to tell you. You're going to have to do your own solutions for the most part. So, like for example, instead of having that bottle all ready to go, okay, mix these guys together and see what happens. You'll walk down the hallway, or you'll be in a fume hood in the room somewhere, all the stock bottles. And there'll be a standard concentration usually very, very concentrated, like hydrochloric acid is like about 12 molar. And if you need a 2 molar solution, you'll have to dilute it. If you need a 1 molar solution of sodium hydroxide, you'll have to measure out how much sodium hydroxide you need, mix it together. You've done this before for specific things, but for the most part, labs, everything's set up for you because we have 45 minutes for the most part to do a lab. Now that we have double periods, we have a little bit more time, but still nowhere near the 2 to 3 hours you'll have for a chem lab. All right, so here's how we're going to do this one. We're actually going to have one bottle that's going to have the standard in it. And you're going to always have to go to that bottle and get that. We're going to make that standard up exactly. We're going to use sodium hydroxide for our secondary standard. We're going to use KHP for our primary standard. All right. We're going to do this lab, and we're going to get very good results, very good percent error, because we're going to do it as if it really mattered. Most of the time, I don't care. We're not going to eat the stuff we make at the end of the lab. You're not going to be selling it on the market. You don't have to worry about quality control. So that if I have bottles all over the place and some idiot accidentally added stuff back to the stock bottle or contaminated it. I mean, how many times do you have, I've noticed, one table throughout the day will have bad results or different results at least compared to the other tables. Well, somebody obviously screwed something up. That should not happen here. All right, you're going to be very meticulous about everything we do, and we're going to take 3 periods, which is basically the equivalent of a normal lab period for college, to do this, because I'm not going to just have everything out for you and let you guys just mix them together and see what happens. All right. Anyway, back to the titration. Let's talk about the actual equation here. It looks very much like the dilution equation, which we've seen before. NaVA equals MVVB. Kind of looks like M1V1 equals M2V2. It's very, very much the same thing. All right. Now, the problem with this, I think everybody can figure out what the V's are, but the N's. Do you remember what the N stands for? It's a measure of concentration, but it's not one we use very often. Do you remember? It's not molarity. It's what? It's normality. Na and NV stand for normality of the acid and base. And we only looked at that when right before we had done lots of calculations with molarity. We've done lots of calculations even with molality and percent solution in Chem 1. But in Chem 2, we've been doing a lot of molarities. I mean, how many times, even in a problem, it'll say, instead of just giving the molarity, it'll say that 25 grams of this and this many milliliters of solution. And you'd have to calculate. We know what molarity is. Normality is a little different, but not much, and I'll get to it in a second. Do you know what VA and VB probably stand for?
Volume.
Yeah, I always get some physics people in here who say velocity.
Idiots.
Yeah, or velociraptor. Now, obviously, it means volume, how much of the acid you use versus how much of the base, VA, VB. Well, let's talk about this normality thing again. Here's the problem with normality, with molarity, I should say. Can anybody see a problem with what I'm going to say here? We just went over the scenario of, this guy's going to be, let's use the same scenario. We took about 10 milliliters of this, and it takes about 20 milliliters of the base. If I know the acid is, say, 2.0 molar, and it took twice as much, then I know what the basis concentration is, right? Not necessarily. What if, matter of fact, let's make the numbers a little bit easier. Let's say it took exactly the same amount of acid as base, and it was 1.0 molar acid. Then you might say, well, the base has to be 1.0 molar too. Makes sense, right? Not necessarily. Here's why. What if the acid were H2SO4 and the base were NaOH? Does anybody see a problem with this?
H2.
Yeah. This guy's got twice as many H's as he has OH's. So a 1.0 molar solution of H2SO4 isn't really 1.0 molar. He doesn't just have 1.0 moles of H ions. He actually has twice as many compared to how much sodium hydroxide has. You see what I'm saying? So a 1 mole, even though they both took up the same amount of solution, what does that tell you? Okay? It tells you this guy's actually a stronger concentration to have matched the two hydrogens per molecule he has there. You understand? So I'm not getting a lot of, anyway. You got that? Make sense? Because he's got twice as many. So all you do to get something called the normality. The normality takes that into account. So you simply multiply by the number of hydrogens or hydroxides per molecule. That's what you do to get it. That takes that into account. So if I have H3PO4 or NaOH or basic versus CaOH2 versus AlOH3, I take that into account in my concentration. That's what normality does. Okay? All right. So that's the procedure we'll eventually be doing, but it's not. Why is it taking us 3 days? Well, most of today is being the notes and the calculate and the formulas, and we're going to mix something up. Most of tomorrow, half of tomorrow, will be getting our primary standardization, because we want to do this right. Normally when I do it, I told you I want to do this as if it really mattered, as if it counted. Normally, if I'm doing a lab and I want a 3 molar hydrochloric acid solution, I just mix it up from the bottle. I dilute it from, if it was 12 molar, I dilute it down to 3 molar, and I say good enough. It's not good enough for real, okay? Basically because hydrochloric acid and sodium hydroxide, neither of those, which are the ones we use most often, are not primary standards. And here's why. Let me show you. Turn that light on. Here's some sodium hydroxide. I'll pour some in here, this beaker. And you can hear, as I shake this beaker around, you can see that they look and they sound very dry. Just dry white pellets. Here's one I poured out just an hour or so ago, 2 hours ago maybe at the most, from the beginning of first period. So how long ago was that? An hour and a half. Notice I could turn this one like that and it doesn't move. I'm going to pass this one around, you're going to look at it. You'll see that there's a little, each one of these guys has got a little ring almost around them. It looks like they're melting. They're not melting. This is not the melting point of sodium hydroxide. What are they doing? They're absorbing water from the air. That's why I've always warned you about, whenever we're using this and other chemicals too, keep the lids on tight. Here's a lid. Here's one that people did not keep on tight years ago. This is from 2006, I think, right? And it's all stuck together. Like if you look at this, it's all stuck at the top there, and it's a big chunk. And if you look at that, it's just a big mess in there. All right. I'm not going to pass this one around, but I'll pass the other one around. You can see how shiny this one is versus how dry. But within a very short time, even by the end of this period, this one will be glossy again, already, start to stick to the bottom. That's how quickly they absorb water from the air. Now, what does that have to do with standardization? I can't just put this on a scale and say, okay, I've got 40 grams of sodium hydroxide in 1 liter of solution. I've got a 1 molar solution. What have I weighed when I put that on the scale? What else have I weighed while it's on that scale? I know that. The water, yeah. Obviously, we zero for the glass. The water, the water. And so it's absorbing water as soon as I open that jar. So what I'm weighing isn't really 40 grams of sodium hydroxide. It's 40 grams of sodium hydroxide in whatever water it's already absorbed. And I don't know how much water absorbed. I have no idea. So that's why this guy's a lousy primary standard. And even worse, they say, okay, well, let's use hydrochloric acid as our standard. We'll know his concentration. Actually, think back to Chem 1. Remember that glass tube had 2 cotton balls, one soaked with hydrochloric acid, one soaked with ammonia. It formed a cloud in the middle, remember? Yeah. Well, I opened that in the Fuma before I did that, and I showed you, just putting the bottles close together, you saw fumes formed and a cloud formed in the Fuma, but you saw it formed here too. Hydrochloric acid, as soon as you open that bottle, is no longer the concentration that it says in the bottle because it's evaporating out. So it's not a question of absorbing water, it's a question of evaporating the hydrochloric acid out. Either way, neither one is correct. As soon as I pour them out, I don't know their exact concentration. Now, there is a way to know their exact concentration. Once I mix them up, they generally don't change much. Like, for example, the sodium hydroxide, once I put him in water and he's dissolved and I've made a solution, he's not going to really change and absorb more water. He does do that a lot with the pellets. Same thing's true with the hydrochloric acid. It doesn't really fume after you've diluted it. So if I had something to compare them to, and that's exactly what I'm going to do in the standardization process, if I have something to compare them to that is not going to evaporate and it's not going to absorb water, and I do have something like that, I have what you're going to make up in a minute, a primary standard called KHP. It stands for potassium hydrogen phthalate, and you don't have to worry about the name of it. But that stuff does not evaporate. It does not absorb water. If you look at the shelf, most of these things have a shelf life. They'll say shelf life. This guy says shelf life good, keep tightly closed. Some things will say poor. they only last for a couple of years before they start absorbing water, or they just break down for other reasons. Other ones will say indefinite, and KHP is one of those that would say indefinite. It really doesn't change much over the years, so you can use that, and it's a good primary standard. All right, now while you're copying this, you turn the light off. This down the definition of what we're doing in standardization. I'll pass this one around and look at the pellets and how they've all pretty much absorbed enough water to almost start dissolving themselves in it. Don't touch it, it's sodium hydroxide. And don't turn it completely upside down. Although they are stuck there, they can fall.
So who left the sodium hydroxide bottle with you?
I don't remember. I don't know. It's years ago.
They're not living anymore, are they?
They may not be. I buried them in the back.
That's on video.
It's on video.
We got it on YouTube.
This one's still fairly dry, but it will absorb enough moisture soon enough. By the end of the period, it won't be able to just rattle those around. That one over there, it'll look like a bench stand. If I let that go to Lamara, there'll be puddles around each of those pellets, a puddle actually of water. They actually dissolve. It's called hygroscopic, and that means they absorb a lot of water from the air. Okay. So we're going to have to, because neither of the things we're using here is a very good primary standard, we're going to have to use a primary standard to figure out their exact concentration. Again, normally I don't care. When we're doing a lab, I'm not trying to we're not trying to sell the medicine we're making and make sure no one gets hurt. We're not trying to worry about quality control for the product we're making. All right, I just want you to learn the concept. So if I make up a 2 molar solution that's really only 1.8 molar or 1.9 molar or 2.2 molar, it really doesn't matter a whole lot to you. But it would matter a whole lot if I wanted to make up a solution, make a drug that I'm going to sell over the counter and kill somebody. All right, it has to be exact. It has to be perfect. I have to have good quality control. Okay, so what we're going to do is we're going to produce a secondary standard. The sodium hydroxide solution will be our secondary standard from the primary. So this is why it takes so long. Today, we're going to mix up the primary standard. Tomorrow, we're going to titrate the secondary standard to get him. And then the following day, well, actually for you, the second period of tomorrow, we're going to actually do the titration. So 2 of the days are just prep, today and the first half of tomorrow.
Now in college, are they just going to tell you like what you're doing and let you go?
Well, sure, absolutely. You're going to have to have read all the stuff ahead of time. You're going to go into the lab, and you'll have 3 hours to complete all of it at once. All right, and there's a lot of waiting around. Like one of the things you'll have to wait around in this first step, when we use the primary standard of KHP, he just doesn't dissolve very well. It takes about 10 minutes or more, maybe 15 or more sometimes, to dissolve our KHP in water. So that's why we're going to spend, I can give you the notes and this part for today. You'll be swirling it back there, and hopefully it'll probably dissolve. Even if it doesn't, it'll dissolve overnight anyway, because it's going to be sitting there. You measure it out, you mix it together, you swirl it up. That takes 15 minutes before you'll see the stuff just kind of keeps going around and around and around in there for a good 10 minutes or more. But eventually it does dissolve, and we'll use him tomorrow to make our secondary standard, which is the NaOH solution. All right, so our eventual goal here, so before I shut the camera off, our eventual goal after we do all of this is to actually do a titration. All right, if you remember back a minute ago, all right, to do this titration with a strong base, that's sodium hydroxide, it's a strong base, and a weak acid, we're going to use acetic acid. All right, but to get to there, we have several things to do first.